Guys, let me just pop open what we need here. Today we're going to be looking at day 12, and last day you're working on combination derivatives and had a couple work days. Hopefully those went well for you. Today in day 12, we're going to look at something called implicit derivatives. So we're going to introduce what I mean when I talk about implicit derivatives. And we're going to look at curves that use implicit derivatives. And then we're going to look at a few examples, some simpler examples today. And tomorrow we'll do another day, part 2 day, where we'll do some more complex examples. So let me just get my clock going here so I can keep track of myself. Okay, there won't be any practice with implicit differentiation until we do both days. This one will be probably a 30-minute video or so, somewhere in that range. Okay, so what I'm talking about, first thing I want to remind you is that we have a couple of different ways to write derivative. Okay, so just to remind you, I'm going to use y prime mostly for this because it works really good. So derivative notations. Okay, we had the y prime, which is the one that we started with. Then we could have, if we could write it as f of x prime as well, because y and f of x mean the same thing. Or we use dy dx, derivative of y with respect to x, when we were doing chain rule, which helped us. And then there's a couple other ones that use capital D's and things like that that we haven't used that you might see in a book. Sometimes they write it like this, dxy, derivative of x with respect to y, if you don't want to write it as a fraction. That was come up with when, back in the old days when it was hard to input a fraction into a typed thing. So they came up with that one. So I'm going to stick with this one mainly, but those are some of the derivative notations that we use. They all mean the same thing. So what we're going to do is we're going to introduce what a implicit derivative is. Okay, so what is an implicit derivative? Okay, so I'll do a little preamble here. So up until now, all our derivatives started in the form of an equation of y equals some expression of x. Sometimes we substituted in, did the chain rule if it was a very complex expression of x. Okay? However, some curves will have values of y to some power. And still be able, and still have a tangent line to them. And we'll just say in brackets, put that. We'll just say still have a possible tangent line. So the curve means that they have a possible derivative. So usually y is not to the power of 1, it's the power of 2 or power of 3 or something like that. Okay, it's a y squared type thing. Okay, when that happens, examples of this that will need implicit differentiation. Okay, so if you have like a circle, I don't know if you know the equate back in the old days before they changed the math curriculum, we used to do conic sections, and we used to do hyperbolas and circles and ellipses and all that, and somehow they took all that out, which doesn't help us in calculus because you've never seen it before. Before then, unless you're taking a AP math course or something. So a circle is usually written as like x squared plus y squared equals some number, usually like a nice squared number, usually r squared they usually have. So that's a circle. And you can still get a tangent to a circle, right? You can also have an ellipse. An ellipse would be something like numbers in front, x squared plus y squared equals some value. I don't know, 64, let's say. So that's an ellipse. Okay, I still wish they would teach sections. You can have a hyperbola, which is the same as an ellipse with a minus sign in between. So you could have like 12x squared minus y squared equals, I don't know, 81. That's a hyperbola. Okay, so circle you know, ellipse you know, hyperbola is like, it kind of looks like this, or looks like two parabolas on the side. And then you can have all kinds of other ones, even just non-curved equations like 2x squared y minus 7xy equals 12. That is a curve, but how do you get the derivative? Okay, so these are all needing implicit differentiation. So what do we do when we get there? So if you see a y with some power to it, so keep on going here. So if you see a y as part of a curve equation to some power, use implicit derivatives. Okay, so so the first thing is the derivative rules are the same. Okay, except when you are deriving y, okay, you multiply the expression by y prime. I'll read some examples, of course. Expression by the derivative of y, so we'll just say y prime. Okay, or if you like, any of the dy dx. This is the other one that we use commonly, or f. Okay, so that is basically the rule. So let's do a bunch of different examples here of how you would do this. Okay, and you have to be careful. There's some tricky stuff in here. Okay, when you just have them adding like this, or like this, or like this, these first three are pretty easy. This fourth one, where you have some multiplication of x and y's together, you have to use the product rule as well. So we'll look at some examples. So that's all we're going to do today, is we're going to look at some examples here. Okay, so let's do some examples. And the first one I'm going to do is just a straightforward, simple one. Type 1, when y is multiplied by a constant. Y multiplied, I better write this out. Maybe I'll type it so it's neater instead of no one likes my writing. All right, so let's type it out. It'll be a little better. Okay, so example 1, y is multiplied by a constant. Now, you don't have to do implicit differentiation of this. You could just divide it out and then figure it out. That's one way you could do it. But it's the easiest type of implicit differentiation that you can do. So my example here, let me get my sheet with my little examples on them. All right, so if I had 2y equals 6x squared plus 2x. Oops, got it on the wrong side here. Here we go. Okay, so if I had 2y, so we got a constant. So instead of y equaling 6x squared plus 2x. So method 1, divide out the constant. Okay, so you could do divide by 2, you get y equals 3x squared plus x. And if you do the derivative of y prime, that's going to be 6x plus 1. Okay, now if we use method 2, implicit differentiation, okay, so the implicit way, I just go leave it as is. Okay, and then when I take the derivative of this, I put a y prime after it. So I go, the derivative of this would be 2, and y would be 1, and then y prime after it equals, and then we get 12x plus 2, and then you would just divide by 2 to get 6x plus 1. So everywhere you see a y, you're going to be doing a y prime after it. Okay, let's do one that is a little more complex with squares in it. Okay, so you have to do a little more complex of a derivative. So in example 2, we're going to be doing with powers of y now. Example 2. Powers of y. Let's do a circle. Let's see here. I should probably put that on another page. Look at that. Okay, let's put this on the next page. All right, so example 2 with powers of y in the equation. Okay, so let's do a very simple one of a circle. So let's say a circle that I had up there as I had x squared plus y squared equals 36. Now nothing is x's and y's aren't multiplied together. So now we just use implicit differentiation. So we take the derivative of this, 2x. We take the derivative of this and then follow it by a y prime plus 2y y prime. Okay, so because it's got the y, we got to follow the derivative using the derivative rules, the power rule, and then the derivative of 36 is 0. Okay, and then what we do is we derive normal. And then here we isolate y prime. Okay, so if we want to isolate y prime, we're going to bring it over to the other side. So we're going to subtract 2y, y prime, because y prime represents a derivative, so from both sides. So we've got 2x is equal to, because we subtracted it there, negative 2y, y prime. Now we've got to divide negative 2y on both sides. And this cancels out, so we get y prime equals negative 2x 2y. Okay, the negative can be there, or there, like it's just negative. Okay, and we can reduce the 2. So then y prime equals negative x over y, because we can cancel that out. And that's our derivative of that circle. Okay, that's a pretty easy one. Okay, so let's do an ellipse or a hyperbola, which is similar to a circle in there. So let's do an example like that. So let's say we had, this is still part example 2, powers of y. So more powers of y. Okay. Okay, so let's say we had a hyperbola there. So we had 16x squared minus 4y squared was equal to 64. Okay, so this is we want to get the derivative of this. So we've got to use regular derivative rules. So 2 times 16 is 32. X, 2 minus 1 is 1, so x. Okay, and then we got to use regular derivative rules here. Minus 2 times 4 is 8. Y to the 1, and then we have to follow it by a y prime, equals the derivative of 64 is 0. There's no variable with it. Okay, so we've got to, we have to isolate this. So let's move the negative 8y y prime to the other side. 32x equals 8y y prime. Divide 8y out. Okay, and we have our y prime. Okay, and we have to 32x over 8y. We can reduce 32 divided by 8 is 3, so that's going to be 3x over y is our if we do our, what am I saying, 3, that's not 24, that's 4x, right? 4 times 8 is, or 32 into 8 is 4 times, because 3 times 8 is only 24. 4x, there we go. 32 divided by 8, 4. Okay, so there is an example of that. Okay, where things get more complex in the final example that I'm going to give you, a couple examples that I'm going to give you today, and then tomorrow we'll do more complex one, a few more complex ones, is what happens when you have equations with multiplication in them. Okay, so we'll do a couple examples like that in our third type examples with powers of y. Now we'll do examples where y and x's are multiplied together. We'll do a few of those. I'm not going to give any practice work today, but tomorrow I'll save, we'll do a couple more complex ones, and then I'll give you some practice work after that. Okay, so let me find one here. Okay, so let's do a very, very simple one first of all. So in these ones, we're going to be looking at examples where x and y's are multiplied. Okay, and so we got to think the product rule. Can't just use the power rule if they're multiplied, if they're multiplied like that. So I'm going to do a very, very simple one to start with, and then I'll do a more complex one after that. And then we'll do some more complex ones tomorrow. And then I'll give you some practice ones as well, because we're at about 21 minutes. So I don't want to go too much longer here. So let's say that my example is 3x squared y. Okay. And I want to get what's the derivative with respect to y, dx dy, or dy dx, pardon me. So the first thing we've got to do, or let's make it a little more complicated. Let's put a cube in there so that we have a derivative there as well. So we got to remember that we can treat this as the first term and this is the second term. So f g prime plus f prime g is what we're going to use. And if we say that f equals 3x squared, then f prime equals 6x. And if g equals y cubed, we're going to get g prime as 3y squared y prime. So then we have to apply this product rule because that's multiplication. Okay, so let's apply the product rule. F, 3x squared, times g prime times 3y squared y prime. Okay, plus, equals, we have to equal to something, otherwise why are we doing it? So let's say equals 0. Okay, because then when we do the derivative of that, it's still 0, or it could be any number, as long as there's no variable there. So then let's say plus, okay, f prime was, where are we here? There's 6x times g, which was y cubed. Okay, so this is going to be equal 0. There we go. Okay, I should have had an equal of something there. Otherwise, it wouldn't be a curve, right? Okay, so here we got 3 times 3, which is 9, x squared, y squared prime. Okay, and that is going to be plus 6x y cubed equals 0. Now we have to isolate this by itself. So let's move this over to the other side. I'll show you how to do this. So first you got to get the term with the y prime by itself. So just put this on the other side. Okay, and then you divide out 9x squared y squared on both sides to get this y prime. Don't forget the prime in there. Okay. Okay, so then I don't need to divide out the y prime on the bottom. I'm trying to get the y prime by itself. Just the stuff that's not the y prime, pardon me. So that means this cancels out and you're left with y prime equals negative 6x y cubed over 9x squared y squared. Now you can reduce this because you can do some canceling. Okay, you can take a 3 out of both the 6 and the 9, so negative 2. We take an x out of the top and then 2 y's out of the bottom. So if we cancel one x there, we're going to left an x on the bottom. If we cancel 2 y's there, we're left with a y on top. Then on the bottom, we're going to have 3. And if we're canceling one x here and one x here, we're going to have an x on the bottom. And we're canceling the 2 y's. So then here is our expression for y prime. Okay, y prime is equal to that. We got to reduce. Okay, so that gets us to about 26 minutes. Tomorrow we'll do more complex examples that have more than one set of multiplications. So you have to apply the product rule more than once. But let's do one more of these. Let's do 2x squared y equals 20. Okay, let's do the product rule for this, so that when we do the derivative of this side, it's going to be 0. But we have to do the product rule here. So f equals 2x squared. So f prime quickly, if we do f prime, that's 4x. And g is y. So g prime is equal to 1 times y prime. So it's just going to be y prime. So that's going to be pretty easy to plug in. So if we're doing the product rule, fg prime, so f is, and then the derivative of this is going to be 0. So we're going to plug the derivative in here. So we've got f 2x squared times g prime, which was just the y prime, okay, plus, now we're going to do f prime, 4x, and then g, which was y, equals to 0 because this is the derivative of that is 0. So then we're going to isolate this on one side. So let's move to 2x squared y prime equals negative 4xy. Okay, and then we just solve for y prime. Divide by 2x squared on both sides. So we've got y prime is equal to, well, negative 4 divided by 2 is negative 2. X divided by x squared is an x on the bottom. And y just on the top by itself. And there is our equation for the derivative of y. Okay, we'll stop there today. I'm not going to give you any practice. That's about 28 minutes, 29 minutes as we're going here. So tomorrow I'll do a couple more examples of more complex derivatives where you have product rules inside of a large curve and they'll be longer. So something like, x cubed plus 3x squared y squared minus 2y squared x plus 8 equals 19. Things like that, which are longer ones. And we'll do a few examples like that. And then probably, I don't know if that's going to take us the whole period. Probably it will. And then probably the next day we'll do the practice for implicit differentiation. And lo and behold, we'll do some slope with line tangent type questions as well tomorrow. And that will take us to the end of the unit. If I look on, I'll just slide this over for you. This is new. I'm updating stuff, but we're about here. So this error will be fixed because I'm redoing stuff. So yes, we'll do a practice day after. So tomorrow will be another instructional day. So we'll see you tomorrow.